Mr. Hollingsworth. Jumping down.
So we conclude the course with you're all having visions of specters and other things. So that the name for this theorem comes from the physics, of course. Now it's for Michael to explain to us what in physics is leading to this name. So you're on call. All right. So the spectral theorem says the following. I'm feeling Math 4000 hasn't let its test out yet. Guess who? Theorem.
Who?
Suppose A is a symmetric n by n matrix. Now, if you wanted to think about linear maps, you would be talking about a linear map with what property?
A transpose equals A.
Well, so the matrix transposes the matrix, but what is it saying about it from the statement with linear maps?
Maybe the inverse is it.
So what fundamental favorite formula do we have? So what does that say? What's Ted's favorite formula from last semester?
XY equals AX transpose.
AX
all transpose
Y equals X
transpose
dot A transpose Y.
So symmetric means,
AX dot Y equals X dot
so that's what we'll say for linear map. So T satisfies T of X dot Y equals X dot T of Y. So if you wanted to think about it just from the linear map perspective, that would be the statement. So suppose you have a symmetric matrix, or you have a symmetric map, meaning this. Then, A, all the eigenvalues of A, parentheses T, are real. It's sort of surprising, actually. B, even if the eigenvalues aren't distinct, you're guaranteed that the matrix is diagonalizable. In fact, there is an orthogonal matrix Q so that using Q rather than P, Q inverse AQ is diagonal, but in fact what's Q inverse if Q is orthogonal? Q transpose. So if I put this back in the linear transformation setting, what are we saying? This orthogonal matrix that you used for change of basis corresponds to a what sort of basis consisting of eigenvectors? What are the columns of an orthogonal matrix? They're more than orthogonal.
Orthonormal.
They're orthonormal. So i.e., there is an orthonormal basis for Rn consisting of eigenvectors. T. So you'll be glad to know one of the main applications of this, aside from physics all over the place, but one of the main applications of this is to go back to high school math. I know that excites you. So I'm going to show you, you may recall that we talked about quadratic forms last semester. We're going to come back to that. So I want to do 2x2s before we go too far here. So I want to do a 2x2 in general before we start doing number crunching so that you see that these things are happening. So what does a 2x2 symmetric matrix look like?
Looks like
Identity.
A, and then B's on the corners, and then D.
Or so A. No, C. Yeah.
Why not? I think it's an E.
Let's not use E. All right, so here's a general 2x2 symmetric matrix. What's the characteristic polynomial?
Minus AC.
AC minus B squared.
Okay. What are the roots?
A plus B, which one? Quadratic.
So do the quadratic formula with these letters, please.
A plus C,
A plus C.
plus or minus square root.
A plus
A
C squared.
A squared.
Minus 4.
1
AC minus B.
With parentheses, right?
2A, not to be confused.
I know,
Yeah.
right, not to be confused. All right, A plus C, plus or minus. Now you may expand and simplify, please.
A squared plus 2AC.
C squared minus 4AC plus 4B squared.
Thank goodness Llama's doing this for me. What did that simplify
Well, you
to?
get an A
A
squared.
squared minus 2AC plus C squared plus 4B squared.
So what was that first stuff?
A minus C squared.
Okay, so if you actually do the algebra, you see you have a square root of a sum of perfect squares. Pretty cool. What does this tell you?
Both are real.
Both eigenvalues are real. So, both real. And when are the eigenvalues equal?
When A minus C equals 2B.
Whoa.
No, wait, that's wrong.
When B is 0 and A
Repeated
equals
root.
C.
So when what?
When B is 0 and A equals C.
C times that.
In other words, it's a multiple of the identity matrix. Not a surprise. You knew that. Just checking. All right? So here's a messy formula, but those are the eigenvalues. How do we find the eigenvectors?
We can have A minus.
Am I really going to take
No, you're not gonna do that.
this and plug it in and do A minus this?
It's just 0, 1, 0, 0.
So if you remember what we did when we did the Fibonacci series, you could sort of finesse the issue and cheat a little bit. So if you look at A minus lambda times the identity, what's a basis for the null space? Oh, okay. E lambda minus A. Did everybody agree with Ken? Okay? All right? Or I could use
C minus lambda.
C. So C lambda minus.
For lambda minus C,
right, you would need to
you need to flip one, yeah.
you would need to take a negative of one of them, right? All right. So what I want to know is, are the eigenspaces assuming distinct roots, in other words, that I don't have a multiple of the identity matrix, are the eigenspaces orthogonal? By the way, does this ring a bell? saying that the eigenspaces for the different eigenvalues should be orthogonal?
Should it?
Mm-hmm. Not for you, because you're a little behind on homework. For everyone else.
The one, what's that? The one where we had the E1, the -1 with the. Yeah, I think that was 24.
No.
19.
No. Older than that.
No, you had that.
You proved in homework that if you had lambda and mu different and you had corresponding eigenvectors for A
Oh,
and an eigenvector for A transpose, then they
Except
were
Y.
orthogonal.
And then same
Remember?
size.
No.
yeah.
But if A equals A transpose, we're talking about an eigenvector for A with eigenvalue lambda and an eigenvector for A with eigenvalue mu, and those are orthogonal. So you've proved it just from this formula that this has to be true. But I wanted to, can we see it from this? So if you took lambda 1 for one of the vectors and lambda 2 for the other, so right, lambda 1 has a plus, lambda 2 has a minus, whichever. So if you took b lambda 1 minus a, and let's say b lambda 2 minus a, I don't know if this is going to work out nicely or not, but we can try it. It doesn't, I don't know if it, I think I'd rather have C in one of them. I think I'm going to use the other one. Lambda 2 minus C, B. What do I get?
Just to expand. C lambda 2 minus BC plus
So
C
you
lambda
get
1
2
minus A. Factor
Looks
out.
like B factors out. So if B is 0, we're already done. Is this right?
But isn't there some to trace?
Yes.
Yeah.
Remember, the sum of the eigenvalues is equal to the trace. So this is in fact 0. And if you don't remember that general fact, what happens if you add the two eigenvalues? You have A plus C plus something, A plus C minus something,
All over 2.
all over 2, so you get A plus C. So you can see it from the formulas as well, but even if you didn't remember the general fact. Okay. All right, so let's do an example. I actually did not make up a 2x2 example, so who knows how the numbers are going to come out. Let's see, can I look at these formulas and make up a nice number? What happens if I look at this matrix?
So we want to find the eigenvalues.
Yes, I want to apply the spectral theorem, and then I'm going to show you how to use it for something.
Okay. So we want the characteristic of
0. It's 0.
I hope not.
The 4 minus 4, which would be negative, return
Yeah.
0. So you're just going to get
What?
2 squared
Yeah,
minus
now you're
5
letting me
t.
T times
Yeah.
Well, t is 0.
Oh yeah, the rank is formed, isn't it?
Yeah. Very cool.
That isn't what I wanted. Although, yeah, it's not what I want for the application. Oh, I see why that happened. Rats. Okay, rats.
Combination.
Rats. give me one.
1, 2, 2, -2. By row.
1, 2, 2, -2. So I'll switch it up slightly.
Oh, cool.
Might have to do some video scrubbing.
Yeah, probably need it. I'd probably need another minus.
That a multiple of the inverse.
Where did the ones come out? Why? Were they horrible?
Hmm? What?
Were
The one you gave me,
numbers?
How they come out?
were they integers, the eigenvalues?
Yeah.
Why don't we just do that one?
1, 2, -2. 1, 2, 2, -2, you said?
Eigenvalues were 2, -3.
Okay, so this should work then. All right, so what's the characteristic? Oh, no. I was actually trying to just do it from that. So what do we get for the lambdas? 1 plus or minus the square root of, no, yes, a minus c.
So 60. Oh, that might be even 7.
So 4 times -2 squared is, yeah, this is what I was trying to do a minute ago. I just wasn't clever enough. 3 squared plus 4 squared, right? This is what I was just trying to do a second ago, but I didn't do it right. Okay.
That's 1 plus or minus 5.
1 plus or minus 5 over 2. So my eigenvalues are -2 and 3. Okay. And we already know what the eigenvectors are from what we wrote up there, so let's save the time and not just go write it all out. The first one is B lambda minus A, so I would have -2, -4, so we could take 1, 2. Does that work? If I multiply this matrix by 1, 2, I'm adding these two columns with a twice here, so I get 2 minus 4 is -2, so it's got to be working. Okay? And what about second eigenvector?
-2, 1.
-2, 1. That seems to be correct. Okay, cool. So it said that I'm supposed to have orthogonal eigenspaces. Do I?
Yes.
That's good. It said I'm supposed to have real eigenvalues. Check. It also said I should be able to find an orthonormal basis of eigenvectors. You'll see why I want that in half a second. Sure, you can always find an orthonormal one, even if you have repeated eigenvalues. So, but in this case, what's my Q matrix? If I want to make an orthonormal basis, I want orthogonal vectors that are length 1, so I divide by square root of 5, since they both have the same length, nicely. And then what do I know? I know that if I take Q inverse, which is Q transpose, times A times Q, I'm going to get the diagonal matrix of eigenvalues. Okay. So what? Well, here's one application of this. Sketch the curve script Q. I'm using script Q to remind you that we had a script Q last semester. I'm going to look at the quadratic form based on this symmetric matrix. So I'm going to take 2x squared minus 4xy minus y squared. and I'm going to set it equal to 6 or 5 or something. I don't care. Let's do 6. So I'm interested in looking at this quadratic equation, which is coming from the symmetric matrix. Do you have vague recollections of this?
How is it coming from a symmetric matrix?
So-
Negative 4xy.
Okay, so recall, Q was gotten by taking the function by taking AX and dotting it with X.
Oh, okay.
So we took 2, negative 2, negative 2, negative 1, X, dotted with X vector. So you get 2X minus 2Y times X. So you get 2x squared minus 2xy minus 2x minus y dotted times y. So you get another negative 2xy, and then you get negative y squared. So you're using these guys as coefficients. The diagonals give you the squares, and the off diagonals give you the cross terms. Okay? So I'll remind you on Friday that we dealt with quadratic forms in one way back in chapter 5. We're going to deal with it differently now. I'm going to try to connect them for you on Friday.
Where do we get the 6?
I made it up.
Okay.
So I'm asking you to draw this curve. Some of you may have learned this in high school. Probably not too many.
I saw it. I have a really painful way of doing it though.
No, this isn't painful. Use what's on the board. So what's on the board? This. This is saying if you rotate coordinates and use this new basis, the matrix becomes diagonal. So in new coordinates, so let's say x prime, y prime, now the question is, how should I get the new coordinates? If I change basis, do you remember this from when we did the change of basis formula? Is x prime equal to qx, or is x equal to qx prime?
The second one.
So we ought to say with x prime equal to q inverse x. So that's, who told me the second one?
Yeah.
So that's this. Let's see what happens. This would mean x is qx prime. So let's write out what script q, multiple q's. So what's the quadratic form? I'm doing ax dotted with x, which you will recall is the same as transposing x and multiplying by ax. Remember dot product, you can think of putting this guy on that side as a row and doing the dot product that way.
You can also use x dot a transpose.
So I want to substitute what a is. From this equation, a is q lambda q transpose. And I want to write this way. And now I'm going to say to myself,
Also does.
this is my new variable. Just like when we did the uncoupling of differential equations, it's the same thing that we're doing here. This is x prime transpose. So I've diagonalized the quadratic form if I use the new coordinates. Because in the new coordinates, what does this become? is just -2 first variable squared plus 3 second variable squared. We got rid of the cross terms. So, true or false, everybody in the room can graph for me this quadratic equation.
I would hope
If you vote true, you better be able to do it.
It'd be easier for sure.
I hope so. Did you guys learn this in high
You
school?
want a right side of 1, so you divide by 6.
So you should know immediately,
It's an ellipse.
it's an ellipse. No, it's not an ellipse.
It's an ellipse.
You have a minus sign and a plus sign. It's a hyperbola. Blah squared minus blah squared equals constant is a hyperbola.
so we had a false thing.
So how do we draw it?
There were like a lot of rules.
So if I put x prime y prime here,
You have the dotted line.
where do the dotted lines come from?
You made a box.
Where do the asymptotes come from?
You made a box.
Where does that box come
So
from?
there's like
The ones had to
a
do
complex
like
degree.
Yeah, there's.
So by the way, the 6 was conveniently chosen
Oh, okay.
if you want to put it in standard form. That's how I chose the 6.
On your box is like the y square.
So think about where asymptotes come from. Asymptotes come from going to infinity and looking at what y over x does. What's the limiting slope? As you go to infinity, either one of these equations works. As x prime and y prime go to infinity, what does the ratio approach? Good guess. Hmm? 1, 3/2, 2/3, plus or minus.
Well, yeah, plus or minus whatever it is.
I believe it's. Well, what does this equation tell me? If I divide through by,
Well, that's what the box is, yeah.
that's where the box comes
You
from.
just set one of them equal to 0 and you draw the lines, and then you have a box, and you just go through the diagonals. And done.
So, if you divide this equation through by x prime squared, you get -2 plus 3 y prime over x prime squared equals 6 over x prime squared. So what does that mean? That means that in the limit, as you make x prime and y prime both get big, y prime over x prime squared goes to 2/3. This goes to 0. So the asymptotes you get by setting this equal to 0 and plotting what that is. You get two lines whose slopes are negatives of each other. That's your box that Cameron keeps talking about.
Well, that's part of the box.
So if you take square root of 2/3 and negative square root of 2/3, those are going to be the asymptotes. Those slopes are going to give you the asymptotes. And what do you observe? You observe that when x prime is 0, you get y prime squared is 2. So you have a square root of 2 and negative square root of 2.
I don't know what the top of the box
And the hyperbola is going to have that as its vertex. And it's going to approach the asymptote. And it's going to have this as its vertex, and it's going to approach the asymptote. So if I drew the picture big enough, you would actually see it.
So that line has a slope of 2/3.
Square root.
Root, yeah.
All right, so I graphed it. Well, doesn't mean a whole lot of good. It's in the wrong coordinate system. Why do we care that we did an orthonormal change of coordinates here?
We can twist it, right?
There's some way to stretch it.
There's some angle if you shift the angle.
Yeah.
So this coordinate system looks how in my usual coordinate system? It's rotated. Right? In the usual coordinate system, I have an orthonormal basis. Now I have a rotated orthonormal basis. So the x prime axis is on the 1, 2 axis. And then perpendicular to it, this is my x prime, y prime coordinate system here. Well, I already know how to graph it in the red coordinates, so I just take this picture and I turn it so that it's in this coordinate system. So I'm not going to pretend that I'm going to do this perfectly accurately here, but you're going to have these two green vertices, and you're going to have the hyperbola looking something like that. And you can put the box in it. I'm not going to take the time to do it. Okay? But again, I'm making the point that the reason this is easy is because you're rotating coordinates. That's what the orthonormal change of basis does. It's not some wacko change of basis. You just rotate the coordinate system.
And how do you know that it only rotates?
Because you have an orthonormal basis.
Right.
Is it not also like stretched by the eigenvalue?
No, the stretching is in the curve, not in the basis.
Oh,
The basis has nothing to do with the eigenvalues. Okay? Yes, sir.
So how did you get x prime and y prime with regards to x and y? From the lambda, big lambda matrix? Or is that just draw this arbitrarily?
it's from the eigenvectors.
Yeah, right. I mean, the Q, the change of basis matrix is telling me the new coordinate system.
Okay. Okay, good.
That's right. So this vector here is Q1, and this vector here is Q2, where those are the columns. Mm-hmm.
And so this is true for any diagonalizable matrix?
No.
Yes, no. Why not?
What's true?
The rotation, symmetric. Okay.
Symmetric.
Yeah.
So if you have any symmetric matrix, there's a rotated change of basis in Rn that gives you the eigenvectors. Mm-hmm.
Does the orthonormal change of basis only hold for symmetric matrices?
Great question. I believe that's one of your homework problems.
And?
It was or is?
It's one of the few on my list to do that I'm not making you turn in. So come back with an answer for Friday. Did everyone hear the question?
Converse of this.
Is the converse. If you have an orthonormal basis of eigenvectors, then your map symmetric, or is the matrix necessarily symmetric?
Why did we consider AX dot X?
Because, well, so we did that same thing last semester because we were interested in understanding second order Taylor series terms. It's a very natural thing. Well, anytime you study quadratic equations of any sort, a homogeneous quadratic can always be represented in that form. So if you're trying to understand linear things, well, we understand those. Quadratic things, now you can understand them. Cubic and higher, harder.
Are there similar methods for cubics and stuff?
Then you're doing higher order tensors. So it's no longer just simple matrices. All right, so the question that you want to think about that Dennis raises is, if you have an orthonormal basis of eigenvectors. In other words, if you can orthogonally diagonalize the matrix, must A. All right, so I will expect an answer on Friday. So on Friday, I'll actually give you a proof of the theorem. That'll only take us a couple minutes. This is not a hard one. And then talk about why it's called the spectral theorem. And then I want to relate it to what we did last semester. But today, let's just do another example. And this one I hope I did prepare. So here's a 3 by 3.
Yes.
And we'll come back to this again on Friday, too. All right, symmetric. Okay, so I'm not going to take the time to work out all the characteristic polynomial with you. I'm just going to tell you what the eigenvalues are. The eigenvalues are, drum roll. Thank you, that's enough. 3, 3, and -9. And you might ask why I couldn't have just done 1, 1, and -3. I could, but then this matrix wouldn't look so nice.
That's true.
So what are the eigenspaces? So let's look at E of 3. So we're looking at the null space of what matrix? What is that? 2, -2, -4. So far it looks good. Those rows are linearly dependent. And 4, -4. Cool. What's the rank of that matrix? 1. What's the dimension of the eigenspace? It had to be.
That's the diagonalizable. So
Eigenvalue 3 had algebraic multiplicity 2. By the theorem, it's diagonalizable, therefore the geometric multiplicity had to be 2. If it weren't at this point,
you messed up.
right, I messed up.
Or a spectral theorem messed up.
Which do you think's more likely?
Challenging assumptions.
So 1, -1, 2 zeros here. Let's review your basic linear algebra skills. What's a basis? Wait, did I screw up?
Yes, -2.
Thank you.
1, -1.
Count on Jackson to keep me honest. Sometimes.
I got you that time.
2, 0, 1.
1, -1.
1, 1, 0, 1, 0. And 2, 0, 1. 2, 0, 1.
Everybody agree that's what our algorithm from last semester gives us? Free variables and all? Why are we annoyed by that basis, if we're going to be annoyed? Not,
It's more than normal.
it's not orthogonal, right? So if we're trying to do what the spectral theorem says and get an orthogonal matrix whose columns are the eigenvectors, what am I going to have to do? I'm going to have to Graham-Schmidt them.
Yes.
Or could you just look at it and say it has to be 1, -1, 1? Is that right?
I'm all in favor of looking and thinking. What are you using?
Instead of 2, 0, 1, 1, -1, 1.
Cool.
Well, let's Graham-Schmidt them for practice.
Instead of using Graham-Schmidt, can we...
Graham-Schmidt should get you that, by the way. If you start with this one, it should get you a multiple of that one. It has to. Because in this two-dimensional plane, if you pick one vector, there's only one direction left perpendicular to it.
Can we, if we cross, and if we had 3 by 3, we cross both of those to get the matrix orthogonal, could we then cross
The vector orthogonal.
vector orthogonal? Yeah. We cross that vector with whichever one of these we like the most, and
You could. I mean, it's good to have internal checks, but
Yeah.
Dave is saying that for E of -9, we'd better get a vector orthogonal to this plane.
I was saying to get the...
I understand. And then having the basis for this one and one of these, you could cross them and get the third. But for E of -9, can anybody see that in their head? What vectors are orthogonal to both of those?
1, -1, -2.
Okay. Good. And And you should be able to check that it's really in E of 9, E of negative 9. If you do one of these, minus this, minus 2. 1 minus 2 is negative 1, minus 8, negative 9. Looking good. 2 minus 1 is 1, plus 8 is 9. Looking good. I quit. It's got to All right. So what's So now if I do my Q matrix, you might say it's not worth the trouble to make them orthonormal, that orthogonal is good enough. And for a lot of things it is, but what does it save you if you have an orthogonal matrix as opposed to one just whose columns are perpendicular?
Not having to stretch it.
But where's the economy of scale here? No pun intended.
Well, it's not scaling. It's just.
Right, so if you want to do the application and rotate coordinates, but also inverse is easy. You just do Q transpose. So yes, you make the numbers a little yuckier, but then inverses are easy. So all right, so if I'm going to make an orthonormal basis, this guy turns into what?
1 over square root. 1 over square root,
And the second guy?
1 over square root 3, 1 over square root 3, 1 over square root 3.
And the third guy?
1 over root 6. Maybe 1 over root 6.
Okay. So I could, at this point, I could give you, again, the associated quadratic form and write down an equation of a quadric surface. So if again, the quadratic form associated to this is going to be what? You want to use x, y, z or x1, x2, x3?
X, Y, Z.
X, Y, Z. All right, so read me the quadratic function, please. Ax dot x.
Okay, X cubed.
Squared. How many xy's?
2.
You've forgotten what we just did.
No, just doing, we did
Oh,
2 by
4
2.
xy's?
So it looks the same. How many xy's?
4.
4. How many xz's?
Also 8.
How many y squareds?
1.
1.
How many yz's?
Negative 8.
How many z squareds?
Negative 5.
Cool. All right, suppose I look at the set of points where this all equals 9. And I ask you, what does it look like?
It's diagonal lines.
So you go through the exact thing we've already done. We've said in the new coordinates, you've got the matrix lambda with 3, 3, negative 9. And so it just becomes the sum of squares in the new coordinates with these coefficients for the same reasons that we did a minute ago. So we're going to get 3x prime squared plus 3y prime squared minus 9z prime squared is 9. And handy dandy, I can divide through and get x prime squared over 3 plus y prime squared over 3 minus z prime squared equals 1. It doesn't really matter. All right, so in the primed coordinate system, what does this look like?
Isn't it a cone?
The asymptote would be a cone.
It looks a little bit like a cooling tower.
Is it a cooling
Okay, so
tower or is it two
It's an
cups?
paraboloidy things.
It's a hyperboloidy thing.
Yeah.
But is it? But the question to decide here is one piece or two.
Well, set z equal to 0, you
have
It was
Zero.
Oh, sorry.
Yeah, z equals 0 to
It's a circle, actually.
Yeah.
you said z.
Z prime equal to 0, you get x prime squared plus y prime squared equals
when z
3.
is
So should
1,
Z-
when,
Okay.
well, wait a minute.
Little thing.
Yeah.
So what's
Yeah, it's one piece.
It's
because
one
it
piece.
puts
It's
me
going to
on
be a
the other side.
hyperboloid that looks like this. So when Jackson said it looks like a cooling tower, he's exactly right. And for those of you who want to think about such things, e.g. when you take differential geometry down the road 20 years from now, this has the property that it's like a saddle surface. Through each point, there's two lines on the surface. And it really is like a cooling tower. They actually build them in this shape because you can build them with rigid metal bars. What would have happened if I had put a -9 here and then had a -1 here?
Yes, and four pieces.
Then it would be two pieces, because when z is 1, you have a circle of radius 0, quote unquote.
When z squared is 1, right. So then you would have two pieces
Z equals 0.
that go like this. This is called a hyperboloid of two sheets. And then if you put a 0 here, it would be exactly like what we did earlier. It would be the asymptote, and that would be the cone.
And then you get to rotate it.
And now you have to rotate it to make the picture in XYZ coordinates. All right, so on Friday, we will prove the theorem, talk about why it's called Spectral Theorem, and then relate it to the LDA transpose we did last semester. And then we're done.